Okay, on number 40, it says the potential energy of an object decreases by 10 joules. What is the change in the object's kinetic energy, assuming that there is no friction in the system? So, conservation of mechanical energy says this. Again, there's no spring, so we don't need to include that in the equation. But in general, and we should know this from yesterday, that whatever potential energy is lost has to turn into kinetic energy. Okay? It can only be one of two things. So if we've lost 10 joules of potential energy, that means that kinetic energy would have had to gain that much, as long as there's no friction. So the answer for 40 is simply just 10 joules. The amount that one type of energy loses, the other type has to gain. On 41, good, these are all conceptual questions here. What is the necessary condition for the mechanical energy of a system to be conserved? As they kind of pointed to in number 40, the necessary condition is that there is no friction, no air resistance. It's a term it's a closed system is the term we like to use. I mean, there's no outside forces, nothing else taking away energy from our system. If there's no friction or anything like that, then the total mechanical energy has to be conserved. And just like we saw in number 40, the total amount of potential energy lost has to equal the total amount of kinetic energy gained. So we'll simply put there no friction. 42. It says, discuss the various energy conversions that occur when a person performs a pole vault. Include as many conversions as you can. Be sure to consider times before, during, and after the vault itself. So, this is actually a really good question. Very good conceptual question. Because there are a lot of different energy conversions we talk about. I mean, technically you could take the energy conversions all the way back to the sun. But starting with the person at rest on the runway with their pole. What are the energy conversions happening? If you want to start there, I guess you'd say that the person's taking the chemical potential energy stored in them and turning it into kinetic energy. So they're standing there with the pole, they start running. So they have kinetic energy. Then, that kinetic energy, and this is literally how you have to do the pole vault, and it's all about how you convert one type of energy into another, Now, in pole vault, what's the ultimate goal? Is to get your body high up in the air. It's to get your body to have a lot of potential energy. Pole vault on the track team last year almost broke the school record. 14 feet 3 inches up in the air. School record's like 14 feet 6 inches and a quarter, just to be a jerk. Went to state. So, point being, that's really high. It's actually a really dangerous event. So, you take that kinetic energy of you moving with the pole, and then what's the next type of energy that turns into? As you're running with the pole, before you get up in the air, you turn your kinetic energy into what? That we just talked about today. So what does that pole do? It bends. Place it in what they call the box there, and it starts to bend. It's very elastic. So you turn your kinetic energy into spring potential energy, or elastic potential energy. So now that big fiberglass pole has bent. It has a natural tendency to snap back into position. You have a lot of stored elastic potential energy in that pole vault then. So again, we're running here. Pole vault pole as they're running. The next step they do, there's a little kind of hole in the ground here by the pad. The next step after that, that pole will bend. And not a very good drawing, but that bending has a natural tendency to then do what? So we went from kinetic energy to spring potential energy. Now what's going to be the next conversion? What's this going to do if they're doing it right? It's going to snap them up in the air. So as this starts to compress, or after this is compressed and it starts to snap back, that's going to lift the person up into the air. So that's turning into what type of energy? Gravitational potential energy. Then they hopefully get over the crossbar and start to fall back to Earth, which then turns into what type of energy? Kinetic energy. So all the energy conversions we have there, we go from kinetic energy of the person to spring potential energy to gravitational potential energy back to kinetic energy till they land on the big mat. Okay. So actually a good breakdown of all three different types of mechanical energy we've had so far. Kinetic, spring potential energy, and gravitational potential energy. Converts through all three. And that is literally what has to happen. You are turning your speed into bending the pole. You're not going to be able to bend that pole very well if you don't have speed, if you don't have kinetic energy. Those things are not easy. They're not very pliable. So you need to have a lot of energy in order to do that. And again, obviously lots of technique involved, but then you turn that elastic energy into take you up in the sky. If you don't do it right, the elastic potential energy will smack you right in the face and you'll hurt yourself really bad. So incredibly technically involved. All right, 43 here. You throw a ball straight up into the air. It reaches a maximum height and returns to your hand. At what locations is the kinetic energy of the ball A, a maximum, and B, a minimum? So, we're here, throw a ball, straight up in the air. So kinetic energy, at what point would you say that it's at a maximum? What's that? At the bottom, like the instant it leaves your hand. Okay? So I guess we don't even need to worry about the time it coming back down. But the instant it leaves your hand, right here, that's when its speed is going to be the highest. It has no potential energy yet. Okay? So the instant it leaves your hand, or I guess if it falls all the way back down to the ground or something, right there. But I don't think that's what they're referring to. The kinetic energy would be at a minimum at what point? Kinetic energy would be at a minimum at the highest point. At the highest point, it stops for an instant. Has no motion, all potential energy. And then the second half of that question says, at what locations is the potential energy of the ball? A maximum and a minimum. So potential energy, that's flip-flopped. Potential energy is at a maximum up here, and at a minimum at the bottom. And that should be a pretty obvious question because potential energy is based on height, and kinetic energy is based on motion, or on speed. All right, moving right along to number 44. Get a few more problems involving some of these guys. At an amusement park, a swimmer uses a water slide to enter the main pool. If the swimmer starts at rest, slides without friction, and descends through a vertical height of 2.31 meters, what is their speed at the bottom of a slide? At the bottom of the slide. Okay, so just like some of the problems we did yesterday, looks like a conservation of mechanical energy problem. Anytime we're losing height, anytime there's changes in height, changes in speed, it's going to be conservation of mechanical energy. There's no spring or anything involved, so we don't need to involve that in the equation. So KEI plus PEG initial, gravitational potential energy, is equal to KE final plus PEG final. So, use a water slide to enter the main pool. la, 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 la. There's your water. Swimmer starts at rest, so VI is equal to 0. Here's our person. Slides without friction, descends through a vertical height of 2.3 meters. What is their speed at the bottom of the slide? Actually, I didn't draw it very well. There's your slide, just the water, whatever. So we want to know V final. Now what terms up here can we cancel out right away? We start from rest, so KE initial cancels out. We have initial height, so that's going to stay where it is. At the bottom, we're going to be going very fast. At the bottom, do we have any height? No, no height left. We've lost all of our height. So that can cancel out. So mg h initial is equal to 1/2 mv final squared. Now, each of these terms have an m on them. What can we do to those m's, Claire? Cancel them out. There you go. Okay, cancel those m's right out. Solve for v final. So v final is going to wind up equaling square root of 2 times g h initial. Or square root of 2 times 9.8 times 2.31. About 6.7 meters per second. Okay, done a few of those now. Hopefully we're getting a little bit more comfortable with problems like that. All right, 45. It says a 2.1 kilogram apple falls from a tree to the ground, 4 meters below. Ignoring air resistance, determine the apple's kinetic energy, its gravitational potential energy, and the total mechanical energy of the system when the apple's height above the ground is 3 meters. Okay? So, here we have our apple. Make some effort here. There's our apple. And it is starting 4.0 meters from the ground. Then it falls to a height of 3 meters. That's what happens when I try to make nice drawings. Apple. Way too much up. Alright. So now it is only at a height of 3 meters high. And it wants to know what the PE is, what the KE is, and what the total mechanical energy is at 3 meters. So, still a conservation of mechanical energy problem. PEI plus KEI is equal to PE final plus KE final. Okay? So PE initial is going to be mass times gravity times height, mgh initial. Okay? It falls from a tree, so KE initial is actually going to be 0. So plus 0 is equal to mgh final. We know all three of those things. Plus 1/2 mv final squared. Now, we don't even need this last term. It doesn't ask for speed, so we don't even need to break that down at all. Okay? So let's just run that backwards and keep that as a KE final. Because since we don't need speed, we don't need to take it to that next step. Okay, so our apple is 0.21 kilograms times 9.8 times our initial height, 4.0. That's our initial potential energy. Or, as the problem refers to it, the potential energy of the system. MGH final is 0.21 kilograms. I'll write in the units so I don't run out of space here. Plus 9.8, or times 9.8 times 3.0. Plus KEF. Okay? So, this is our initial potential energy. This is the potential energy of the system. So 0.2 times 9.8 times 4. So we have 7.84 joules is equal to 0.21 times 9.8 times 3, 6.17 plus KE final. Okay? So KE final is equal to 7.84 minus 6.17. Yeah.
I didn't get that for
Quick correction there, it was 8.23. 8.23 joules. We gotta correct that over here. Just start that all over. So, KE final is equal to 8.23 minus 6.17. 2.06 joules. Okay, so 2.06 joules is our, we look back at the problem here, is our kinetic energy. It also asks for the gravitational potential energy of the system. The gravitational potential energy of the system is 6.17. That's what our PE is when we're at 3 meters. And the total mechanical energy of the system is this much. So this is your total mechanical energy, just the total from one side. This is the PE at 3 meters, and this is the KE at 3 meters. All right, and we'll skip 46 for now.